Okay, good morning. How's the homework 3 going? Is it pretty straightforward? Any confusion about those two different ways of doing the same thing? Is it good? Okay, it's due today, right? Yeah, so don't forget. All right, so today we are on lecture 19. And we've been talking about the symmetric airfoil design using Profoil and M-foil. And we're going to continue that. So in the last class, where I stopped was with an example 6-segment symmetric airfoil. And because this is symmetric, you only need to define 3 of the segments. If you do it on the upper surface, the lower surface is going to be mirrored, right? So we talked about how the phi values for 1, 2, essentially define the phi values for 4 and 5. And this is 30, this is always 60. And also the alpha stars for these 3 segments are mirrored on the lower surface. So we talked about how you need to write the foil lines only for, there are 6 segments, but you need to put the foil lines only for 3 of them, because if you put the foil lines for these 3, these are automatically generated by Profoil. And that's a huge benefit, because if you have to constantly mirror these and put the lower surface segments, it's not only very user unfriendly, but it's also gives rise to the possibility of mistakes. Okay, so we'll take this, the latest symmetric airfoil file, and we'll make some changes to see what happens. Okay, so let me go to my I'm going to open up this 4-segment airfoil, and let me start M-foil. So remember, when you want to start M-foil, you always go to the M-files directory, and then from there in MATLAB you type M-foil, and it'll ask you to choose the airfoil. I'm going to choose the symmetric example. No, symmetric 4-segment 1. Okay. So this 4-segment airfoil that I have in the editor, I'm just using the MATLAB editor, and you can use this too, or you can use some other editor. Normally I use Emacs on my own desktop, but because I'm using the classroom computer, I'm going to use the MATLAB editor, because I don't have the Emacs here. So like we have seen before, it opens up these 2 windows. So the phi for the first and second segments are 14.5 and 30, and that's what this this airfoil has. This is about 14.5 in angle coordinates, right? In XY coordinates it will be here. This is the leading edge, and then this is the lower surface. Automatically it mirrors it, and the alpha SP line has two values, so it's going to plot the velocity distribution at 0 and 2. Okay. Now let's do a few things. So the alpha star for these segments are 6 and 6. Let's change them and see what happens. Okay, so today we'll start with the sim underscore force segment 1.dat.in, right? I think I might rename this when I actually give it to you. I might call it demo or something like that. Oh, there is a file called, yeah, let's call this force segment demo 1. So this is the input file. Hold on 1 second. Right. So this file has got 4 segments, and it's a symmetric airfoil, so you only need to give in profile you only need to give 2. Phi here is 14.5 and the alpha star here is 6. The alpha star here is also 6, and the lower surface is automatically defined in profile. Okay, so we'll start with this, and I'm going to do a couple of things which are going to be difficult to explain right now. So let me just do it. And is it running? Okay. Oh no, yeah, I should actually go and change the profile.in. That's the mistake I did. So I want to edit this, right? I have to edit the profile.in in the work directory. I mean, I was explaining that two lectures back and I forgot to do it myself. So I want to comment out this Newton line, which we haven't talked about yet, but okay, so this is what happens. You get a really thick airfoil. Okay, so this is what you will get. This is the airfoil you will get when you just specify these alpha stars. Alpha star equals 6 on both these segments. So you know the way alpha star works is if alpha z equals that alpha star, then you should get a flat velocity distribution on that segment, right? So I'm going to make profile plot the velocity distributions at 4 angles of attack, 0, 2, 4, 6, and so I should remember to change this to 4, and then let's run this again. So these are the velocity distributions for 0 degrees. 0 degrees on a symmetric airfoil, both the upper and lower surfaces will have the same velocity distribution, right? So this plot is, this line is both the upper and lower surface. So the gap between those lines is 0. That's because it's producing 0 lift coefficient. 2 degrees is this. This is the upper surface, this is the lower surface. 4 degrees is this, and then 6 degrees is this. So there is, if you actually zoom in, you'll see that some of the triangles point up. That's just to indicate that those are upper surface, and some point down. These are lower surface velocity distributions, and on this both the upper and lower coincide, so you have both the triangles. So if you want to zoom in, this figure will automatically let you zoom in, so you can zoom in like this, or you can click and it will zoom in this way. Same way for the geometry, you can zoom in. You can either zoom in like this or draw a little rectangle and it will zoom in. So anyway, does this make sense? That the 6 degrees is actually has a flat, on this segment the velocity distribution is flat. Now the airfoil is really thick, right? So let's make a change and see what happens. So I'm going to, so let me save this. I'm actually going to call this the save file. I'm actually going to call this the demo1. forseg demo1.in. Okay. Now instead of 6, let's make this 4. So I'm going to make the alpha star for the 2 segments as 4 degrees. What will happen to the velocity distribution? What is the one thing that you can say will happen?
There will be a flat line on the second one on the top.
Right. So from the top, the second line is the upper surface velocity distribution for 4 degrees. Right? That will become flat now. What will happen to the 6 degree? It will become adverse, and I mean rest of it will be whatever they turn out to be. So let's save this and let's run this, and that's what you see happening, right? So we are seeing a bunch of things. First, we see that as we expected, the 4 degrees velocity distribution on the upper surface, segment number 2, is now flat. At 6 degrees it becomes adverse as expected. Second thing is, I've mentioned this before, M-foil always shows the previous iteration and the current iteration. So the dashed white lines always correspond to the immediate previous iteration, whatever you had, right? Both the geometry and the velocity distribution. And the green line is the latest answer, latest airfoil. So that's the second one. The third one is, anytime you change alpha star, especially a change like this, that will also change the geometry, right? Obviously, the airfoil geometry has to change in order to produce a change in the velocity distribution. But the nice thing about inverse method is you're not thinking in terms of geometry, you're thinking in terms of velocity distribution, and the method will just give you the geometry that will satisfy the desired velocity distribution, right, or desired alpha star. So it turns out that when you reduce the upper surface alpha star, which is what we did, the thickness reduces. So then you can say then that one way to control thickness is to vary the alpha star, right? So there are times when you have to design an airfoil of a certain thickness. I mean, many times that happens, right? You usually have a thickness constraint, and somebody will say design a 12% airfoil, and you have to do it. So in this method, the way to achieve thickness is to vary the alpha star too. I mean, at one point you have to give up on something. So you may, if you have to get the thickness, you may have to give up on exactly what you want in aerodynamics and you get thickness. But then that's a lot of iteration, right? We don't know what the thickness is. I mean, we can go to the MATLAB window and it tells us that the thickness is 18.6. So this latest airfoil is 18.6% thickness. But that's a lot of trial and error. So if you want 12%, you have to now fiddle around with the alpha star and keep on fiddling around till you get 12. So there is something called a Newton iteration built in Profoil that will help you automate that. So we'll come to that. But first, let me summarize the main things that we have seen by changing alpha star. So so the earlier airfoil was 21.04% thick. Is 24.01% thick as per the statistics . So in the MATLAB workspace window, every time Profoil runs, it prints out the statistics. So I just scrolled up and the first demo that we did, the airfoil is 21.04 or 24.01% thick. So these are the statistics that Profoil writes after every time you run Profoil. So this is for the demo 1. Now what we did is we reduced alpha star on segments 1 and 2 to 4 degrees. So instead of 6. Right? So we noticed, okay, so first of all, this in the first demo, it is we see that at alpha z equals 6 degrees, and because this is a symmetric airfoil, alpha z is the same as alpha, right? Angle of attack relative to 0, zero lift angle is 0. We see that alpha is at segment number 2 has flat velocity distribution. So when you make the change, we see that now segment number 2 has flat v-dist at alpha z equals 4 degrees. And v-dist at alpha z equals 6 degrees is now adverse. So let's say I like this airfoil or I want to save this airfoil. I can go now and save this airfoil to the same folder instead of demo. Sorry. I'll have to repeat this. I forgot to change the screen. Okay, so suppose I want to save this. I go to File, Save File, and instead of 4 segment demo 1, we'll call this demo 2. Okay, so I'll put all these files on Moodle so you can actually go through this if you like. So we'll save this as sim underscore 4 segment underscore demo2 .in. Okay, a few other things we saw is that so curves for velocity distribution, geometry, alpha star distribution. We have not really started looking at the alpha star distribution, but this will be the same thing. For current iteration, when I say iteration, I mean design iteration, not the Newton iteration that we're going to talk about. So the current design as solid green line, and for previous version or previous design as dashed white line. And upper surface segment markers are upward facing triangles, and lower surface markers are downward facing triangles. And then the other thing we saw is when alpha star on upper surface is decreased, the airfoil okay. Did we notice anything else?
0 degree has
Yeah, the 0 degree has a common line. That's because it's a symmetric airfoil. So because this is symmetric airfoil, you know, I'm pausing because this is the page 18-9 from the previous lecture. I'm wondering if this should be negative. So the lower surface will be negative 11, negative 9, negative 7, right? Let me think about that as we go forward. Okay. Yeah, because this is when you decrease upper surface alpha star, you automatically increase lower surface alpha star by the same amount to maintain symmetry, and that's why I'm starting to wonder if this should be negative, I believe. I'm just, okay, let's do this. Okay, let's talk about this window. So there are two windows, right? There is the geometry and velocity distribution and the alpha star distribution. Okay, so what this window plots is the upper surface alpha star distribution as a function of phi, or you can toggle it, and this is a symmetric airfoil, so you can't toggle it. Or you can plot the lower surface. In a cambered airfoil, you can toggle this and go to lower surface and plot that. For a symmetric airfoil, all you have to do is define the upper surface and everything is automatically defined. And so what is here is, again, the dashed white line is the previous airfoil, the current one is green line. So even here you can zoom in, and when you zoom in you'll see that this was 6 and then you made it 4 and it's come here, right? Now, okay, I'm going to do something to remind myself as to whether the lower surface alpha stars will be negative. So just bear with me for a moment. We haven't talked about this, so you won't understand what I'm doing. Oh gosh. Yeah. Now if I load this, how do I load it in MATLAB? Yeah, it should be negative. Okay, I confirmed it. Okay, so there's a correction. So we have to go back to lecture 18, last 2 pages. And so I just kind of blanked out about this in the last class. So when the upper surface alpha star for any segment is some value, this for a symmetric airfoil, the corresponding mirrored segment of the lower surface will have negative of that number. So if this is alpha star of 7, this will be alpha star of not 7, it will be minus 7. Okay, so I have to somehow mark this as a correction. Like that, this segment is alpha star of 9, and this will not be 9, it will be minus 9. And similarly, this segment will not be 11, it will be minus 11. Right, so that kind of makes sense, right? If you have a symmetric airfoil, if this segment at 4 degrees, if it becomes flat velocity distribution, on the lower surface it will have to go to minus 4 for it to become flat. So it's got to be minus 7, minus 9, minus 11. And like that, these segments will be minus 11, minus 9, minus 7. So please make these corrections in your notes for lecture 18. So now we can kind of understand what's going on here. So when you take an airfoil like this and you change the alpha star, let's say you change this alpha star from 9 to 6, you decrease it by 3 degrees, right? It's a symmetric airfoil. So automatically this will, from -9, it will become -6. So if you decrease this, this will increase, have to increase by the same amount because it's a symmetric airfoil. In a cambered airfoil, that won't happen. It won't happen automatically. If you want to do those things, you will have to do it consciously. What you do for the upper surface, if you want to make that change for the lower surface, you'll have to do that. So we'll talk about the cambered part later. Let's just do the symmetric now. Okay, so does this make sense? Okay, so what we see is that alpha star is actually a nice control for the geometric parameter thickness, right? So if you say the new airfoil, so the new airfoil thickness is what was the new airfoil thickness is 18.6. The new airfoil, by which I mean demo 2. And I know this from profile statistics. When I say profile statistics, these are the numbers that are listed at the end of the profile run in the MATLAB window. So suppose I want to make things easy and I say I want an airfoil that is 12% thick. Okay, so we know the control for that. You know, so the alpha star is like a knob. You can change that and that will change thickness. Except that if you want a certain thickness, you don't want to keep on fiddling with that knob till you get it exactly, right? There must be an automation. There is an automation in profile. So that's what we are going to talk about, and that's this line. So these will start to become clearer as we go along. So let's just focus on one thing. Let's understand that, and then other things will start to fall in place. So there are these lines called Newt1 G0 and IDES. There's one here and there is one here. I've commented the second one out. In demo 1 and demo 2, these two lines are commented out. So an exclamation point means commented out. So profile will read it, but it won't do anything about it, right? It's like a code that you comment out. This is a way to tell profile to go and do a Newton iteration, Newton-Raphson iteration, if you want to call it that. Some of you were in applied aero last semester. You were in applied aero, right? Has anyone taken applied aero? Okay, only one. Anyway, we talked about Newton-Raphson there, right? The F0 in MATLAB is essentially a Newton-Raphson. So with this line, you can tell profile, go change some knob, and there are many knobs in profile. We have just talked about one knob so far, which is the alpha star knob. You can tell profile to say, hey, this is a knob, go change that knob to get me something that I want in something. It can be thickness. So this example, we are going to see how you tell profile to go change the alpha star knob to get a thickness that you want. And so I'm going to uncomment this. So let's ignore this Newton line. It's a little bit more complicated. We'll come back to it later. Let's leave this alone. We'll just talk about this part. So I'm going to uncomment this. And all these keywords mean something, and I will give you a sort of cheat sheet that tells you what all these numbers are and how to manipulate them. Right now we are just going to say, let's let's tell Profile that I want a 12% thickness. That means thickness to chord of 0.12, right? And these keywords 6, 300 means go change the alpha star knob essentially. And 0.5 is something called a clamp that's used for Newton iteration. Just again, don't worry about it too much now. We'll talk about it in a few minutes. So when I uncomment this and put 0.12 here, Profile will actually go and change the alpha stars to give you 12% thickness, right? So let me save this. I've done that, right? So I'll go here. I'll say run Profile, and it actually did it. So that you can go now to the statistics, and thickness max is exactly 12%, which is a huge convenience for a designer. You don't have to manually fiddle around with some knob to get 12% thickness. And this is not the only one. You can have many Newton iterations. You can go and say, Profile, go change alpha star to give me this thickness, go change something else to give me that camber, go change something else to keep the velocity distribution flat here, do this and do that. And it'll do all of those things. It's like it can manipulate, let's say, 6 knobs to give you 6 different things. Imagine if you had to do that yourself, because all these knobs interact with each other. So when you go change alpha star to get thickness, something will happen to maybe camber. In this is symmetric airfoil, but so camber is not a problem. But in a cambered airfoil, then if you go and change something to make camber, then thickness will go away. Now with the multi-dimensional Newton iteration, you're saying, go fiddle around with all these knobs, do whatever is needed, give me this thickness, give me this camber, give me something else, give me this and give me that. And it'll, if it converges, it'll give you all of those things, which is really, like, that's what you want a computer to do. You don't want to be doing those things by hand. So it figured out that alpha star has to change by some amount, and we can see what amount here. This is confusing. Let me run this again. Yeah, okay. So I have to tell you about these symbols, and I'll talk about that shortly. And it figured out that this is the airfoil that you need to have. It's changed alpha stars, so approximately you can see that alpha star has got to be around 2, right? Because 2 degrees is almost flat. Not exactly flat, but so alpha star for this segment is approximately 2. It had to go and figure that out. In fact, it won't be exactly 2, it'll be something else. So so before I do that, in this page, let me go and write this as, note that in both demo 1 and demo 2, the so I used an exclamation point. These 2 files have that exclamation, have these lines, but they're commented out. So Profile ignores them. No, 19-3. Newton iteration, which is pretty much the same as Newton-Raphson. So okay, so that line looks like this. So here is the syntax. So we call this Newton line, right? It's just a line in the input file that tells Profile how to do the Newton iteration. So that line looks like this, Newt 1 G0. This is 0, not O. So not alphabet. So Newt 1 G0, 102, and then we wanted desired thickness of 0.12, and then 6, 300, and then 0.5. So the meaning of Newt 1 G0 is it's a one-dimensional Newton iteration. That means one-dimensional means one variable. That means go change one knob to get something else, right? Some other one thing. There are multi-dimensional Newton iterations where, and I don't think we'll ever get into it in this course, this is much more advanced stuff which takes a lot of experience with Profile before it even is useful. You can do almost many things with what we do in the course. A multi-dimensional one is where you change several knobs at the same time to achieve several different things. So, I mean, right now, let's not even think about that. Okay, so 102 means, and this is how Profile has been coded, right? So these are keywords that are coded into Profile in the Fortran part. 102 means you're telling Profile, hey, go and achieve a certain thickness to chord, maximum thickness to chord ratio. And 0.12 means this is the desired T over C max of 12%. 6 and 300 means the knobs. You are essentially telling what knobs you want Profile to use. Increase alpha star and decrease or increase alpha star on upper surface and decrease alpha star on lower surface by the same amount. And this is called a clamp, and or you can think of it as damping factor for the iteration. So as far as your projects are concerned, we'll go into some more details on all these Newton iterations, and I'll give you more info on the syntax. But a lot of these lines will already be there in the sample files I give you. So you just have to go and change those numbers. And as long as you understand what those numbers are, it should be straightforward. Now, so we did this, right? And then we have another line called IDES. This essentially means you're telling profile so in this line you're just telling what knob you want to control to achieve what parameter and what value, right? You're saying go change the alpha star knob to get a thickness of 12%. You're telling that, and then here you're saying, okay, now go do it. Here you're giving the specification, here you're giving sort of like the command to actually go and implement it. So what does profile do? The clock is wrong. Okay. So profile actually goes and changes the alpha star. So that means the input alpha star you gave, in our case it was 4 degrees, right? We said 4 degrees on the upper surface minus 4 degrees on the lower surface. That's not going to be true anymore. It'll go and change it. So now input and converged So let's look at the alpha star window. Window means the plot window in MATLAB. So as always, green is current airfoil and white equals previous airfoil. And the alpha star syntax or the plot legend is like this. If you have circles, that's the input. And the line with the triangle, upper facing triangle, is converged alpha star distribution for upper surface, and with a lower facing triangle is converged alpha star distribution for lower surface. And there's a file called profile.dmp in mfoil/work. And this file has the converged alpha star distribution. Okay, so let's go and see these things on the computer. So let's look at the okay, let me do this. I'm going to go back here, comment out this. Oops. Comment this out, and I'm going to remove this. I did something to, let me load this again. Okay, I'm going to load the file. And anytime you load a new file, it'll say, hey, if you load a new file, you'll overwrite the profile, you'll overwrite the current airfoil. Are you okay with that? And right now I'm okay with it. I'm going to proceed. And I'm going to choose demo 2. I'll open it. And this is demo 2. Right? This is where we were before we uncommented this line. Now I'll uncomment this so that we'll be exactly where we were when we started. The so this is that very thick airfoil, 18% thick airfoil, and once I uncomment this and make it 12%, so I'm starting the Newton iteration to make it a 12% thick airfoil. And I'm going to run profile. Did I save this? Yeah, I saved this and I run profile. So this is what you get. So this is the new 12% airfoil. And we saw this just a few minutes back. So now let's focus on the alpha star. What we see is that there are a few things going on here, and that's why this is a little cluttered. So this line has got a green circle symbol. That means that's the input. We started off with an input of 4 degrees, and then it varied the alpha star and figured out that something like 2.2 or whatever. 2.2 is what is needed to get 12% thickness, and so this is a green line with the triangle. Right? So if I run this again, the old airfoil will go away and it will become a little clearer. Yeah, now you can see that there is a circle symbol. I don't know if you can see that clearly from there, but when you run it, you will know this. There's a circle symbol, that's the input, and this is the converged, and this is a symmetric airfoil, so there is no lower surface. Lower surface is just the same as, it's the mirror of the upper surface. So the converged alpha star distribution will be in profile.dmp. So let's open that. Profile.dmp is in work, and you can see profile.dmp will have only a few things. It will have the foil lines, it will have these FES, REC, VLEV, and ILE. We haven't talked about those things yet, so don't worry about them. But basically, this is the main thing that I want to talk about. So this is the converged alpha star. It figured out that it needs 2.07826, whatever, right? That's where the knob should be set to get 12% thickness. So this is kind of useful to remember. If you want to know what the alpha star is, you can go to profile.dmp, and you can actually copy this back into the main file. And then even if you turn off the Newton iteration, if you don't change anything else, you will get exactly 12%. Okay, so any questions so far? Some of this will start becoming a little familiar and intuitive after you start using it. So let's let me talk about project 1. I'm going to hand out project 1 today. Project 1 builds on homework 3. So you'll be finishing up homework 3 today, right, by midnight. So then you can start on project 1. And project 1, in this you will be the objective will be to design symmetric airfoil using Profoil and M-foil. Along with X-foil for analysis. So usually with Profoil you need some analysis tool to go and get drag and all those other things. So in this project 1 you'll be designing 2 airfoils. One for each speed. So you have 2 speeds, right? Even in homework 3 you have 2 speeds. So you'll design 1 airfoil, and this always confuses everybody. So just remember, I think I've made it really clear in the project 2, but still there's always questions. So you're designing 2 airfoils, 1 airfoil for 30 meters per second, and second airfoil for 60 meters per second. And your problem is very similar to homework 3 in some ways. You have to design a symmetric airfoil to go around this fairing or around this antenna, and this height is 2.5 centimeters. And that's all is given, right? You're given these 2 speeds, you're given this, and each, and your objective is to minimize drag per unit span for the first airfoil at V equals 30 meters per second at alpha equals 0 degrees and 2 degrees. So this is, so first objective is this, second objective is do the same thing, minimize d prime for the second airfoil at V equals 60 meters per second at alpha equals 0 degrees and 2 degrees. Okay, so there are 2 airfoils. One is designed only for 30, the other is designed only for 60, but each one at its respective speed, you're trying to minimize drag for 0 degrees and 2 degrees. The reason why you're trying to do it for not just 0 degrees is, let's say you want to design a fairing for some object, like in the very first lecture I showed the AeroVironment Centurion, the solar powered airplane with those pods, right? Those pods contain avionics, and so that's usually symmetric airfoil because it's in symmetric flight. But although it is nominally at 0 angle of attack, the airplane is going to be having side slip and some perturbations, and it's going to be doing some maneuvers. So you don't want an airfoil that's really optimized for 0 degrees, and then at like half degree angle of attack it just causes like some huge drag increase, right? Because nothing is going to operate perfectly at 0. There will be always some oscillations of the airplane or some atmospheric turbulence. So angle of attack is going to always vary a little bit, plus minus 2 degrees or 3 degrees or something. So we're going to assume it's something like 2 degrees. So this airfoil shouldn't be extremely low drag at 0 and then have a high drag increase at like 1 degree. So we want it to have a range of angles over which it is well behaved. And we're going to say if it's well behaved at 0 and 2, probability is it's going to be fine in between. So we're going to use 0 degrees, 2 degrees. Airfoil 1 at this speed, airfoil 2 at this speed. And in order to keep all of this in some tractable fashion, I have created a figure of merit, and okay, let me try to pull up this project too while I'm talking. No, it's not here. Gosh, what happened to it? They've got all these two-factor authentications all over the place, and it's like you can't get away from your smartphone. What happened to it? Yeah. Okay. Okay. So I'll put this shortly, but basically this is the figure of merit is 1 over d prime average. No. So this FOM equals 1 over d prime average. D prime is drag per unit span, right? So you'll have 4 drag per unit spans. For airfoil 1, you'll have drag per unit span at 0 degrees and 2 degrees at 30 meters per second. Airfoil 2, you'll have drag per unit span again at 0 and 2 degrees, but at 60 meters per second. So if you take the average of all those, so that will be like 1 over d prime average is d prime, let's say v equals 30, alpha equals 0, plus same thing, v equals 30, alpha equals 2, and this is airfoil equals 1, foil number 1, this is foil number 2, plus this is also 1. And then v equals 60, alpha equals 0, foil number 2, plus d prime V equals 60, alpha equals 2, foil number 2. And 1/4 of this, that's the average. So, I mean, this is just something I have sort of, let's say, cooked up to give you some number that you're always going to try to maximize. And so this confuses people, and I think it's a legitimate confusion. It's like you're designing 2 airfoils, right? But then I'm creating 1 figure of merit. What does that mean? Like, how do you take 2 different airfoils and create 1 figure of merit? And the way I think about this is not a figure of merit for one airfoil or the other. It's a figure of merit for you as a designer. So as a designer, you try to keep on increasing this figure of merit, and wherever you get the maximum, that's your best effort in this project 1. And remember, for this 1 figure of merit, you're juggling with 2 airfoils, and each one you can keep on designing, right? You can keep on tweaking. So this airfoil, this foil 1, you can keep independently improving it, and independently you can improve foil 2, but then you take the best foil 1, best foil 2, and put them all together in this figure of merit and try to maximize that. So one way to know if you're doing at least reasonably well is in homework 3 you're using the 0012, right? NACA 0012? No, what is some baseline airfoil I gave you? What is that? Which one did I didn't give you the name, I just gave you an airfoil, right? Okay. So that is some stock airfoil from some catalog. So you got to do it at least better than that. When you're designing a custom airfoil, you should do better than some airfoil pulled out of a catalog. So one thing you could do is you can pretend the airfoil that I gave you for homework 1 is both. Suppose you use that for both foil 1 and 2. You can go and create the figure of merit for that airfoil. Clearly you should be better than that. Okay, so that's when you know you have at least crossed the minimum threshold. After that, it's just how much intuition you have about designing airfoils based on all the things we talked about, how much time you put into it. And I may be able to look up and tell you some typical FOMs that students have got in the past. I don't remember offhand. But this is one of those things that some students just go nuts over this. And usually actually in the past there have been some undergrad students who also took this course, like in the senior year. And for whatever reason, they just go crazy over this. They work like several nights and they just beat the whole class with some very high FOM. So this is not like a real competition or anything. So don't, I want you to put in some good effort, but don't get super stressed out. It's not like I'm going to give grades based on who comes first and who comes second or something. This is more of a typical type of symmetric airfoil design that you might do if you have to go and design a fairing. In fact, I've done these kind of problems for real life airplanes. That pod airfoil I designed for the AeroVironment Centurion was basically a problem like this. In fact, that was more complicated because here I'm saying, let's assume an antenna of 2.5 centimeter height. Right there, they gave me a rectangle. I mean, in real life, the avionics will be in a box or something, right? So it's not at one point that I have to make sure the airfoil clears it. I have to clear it over a region. So this is actually very similar to a design problem, except that I've created this fictitious figure of merit, and that's just to keep track of a number that you can keep on improving. But this is also time bound, right? So you keep doing this within the time you have, and at some point you say this is the best I can do, and you write it up and submit the project. So I'll post this. We'll talk a little bit more about this as we go and let's see, I don't have much time today. So in the next class, we'll talk some more about some kind of a process for this. There is no one way to do it, right? There's no one correct answer. And there is no one procedure or anything like this. This is very open-ended. So I can maybe give, what is that noise? Oh, yeah, it's my 2-minute alarm. I changed the alarm tone, the ringtone, and it was like, what? I forgot what it was. Anyway, so there is no one procedure, but I will give a suggested procedure so that at least you have some outline if you want to follow that. But there is also a lot of room for your own design intuition. And you can see, for example, if laminar separation bubbles are occurring, then you can do this to velocity distribution and all that. And we'll also move away from a 4-segment airfoil. The 4-segment airfoil is basically for demonstration purposes. In reality, you will have more segments which will give you more control over velocity distributions. So in the next class, we'll talk about an airfoil with many segments and how you can use the alpha star window to actually go and sort of, you can go click, 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 click and draw an alpha star distribution and say use this. So we can do that. So I'll talk about that, and I'll also give you a starting point for I'll give you a profile file for an airfoil with many segments. So if you like, you can start with that, and it will have the Newton iteration lines. So you can go vary the thickness in that and do all that sort of stuff. So I think it will start becoming familiar. So in the next class, we should be all done with the discussion for project 1 and you can move forward. Okay, thanks.